I'm going to do a classical derivation of the ideal gas law. So PV equals N KT, where we have the pressure times the volume equals, this is the number of particles, Boltzmann's constant, and the temperature. You may also see it as little n, and then RT, where this is the number of moles, and this is the gas constant. Just a different way of putting it. And we're going to do this on classical, through classical considerations, just treating the particles as little point masses that bounce off elastically from the walls. So we're basically just going to take the average force exerted on the wall by the particles, and then we'll be able to get this ideal gas gas equation out of it. So one thing to note is that the energy of an ideal gas is given by this, where we have, again, the number of molecules, and then KT, and this, by the equipartition theorem, is 1/2 of KT for every degree of freedom. So because there are 3 dimensions and n molecules here, or particles, there are 3n degrees of freedom, and so there's 1/2 KT worth of energy for each degree of freedom. And we're, because we're only going to be looking in sort of half of 1 degree of freedom, meaning particles only moving one direction, there's an extra factor of 2 that comes into play here. So we'll go ahead and just draw a box. And so this will be our volume V with n particles inside of it. And I'm going to call this side A, and we'll be talking about this direction X, specifically the positive direction of X, because we're going to be talking about the particles coming along in the positive X direction and then striking this side A of this box with area A. Alright, so let's see, we can start by considering a small, we'll do this in a different color, a thin portion of this box. So we're just going to look at the slice here, and it has some tiny width, and I'm going to call that delta X. So we'll be looking at the particles inside this little slice, and the force is the time derivative of momentum. So this is momentum. So time derivative, or in our case, I'm going to go ahead and make these some small finite quantities here, a delta t and a delta v momentum. We could probably just do this with the infinitesimals as well. But so what is this delta t? Well, it's just this delta x here. So we're going to velocity in the x direction, because so this is how long it takes particles delta x away from the wall to move towards the wall and to hit the wall. All right. So we also need to find an equation for this Vx. Let's see if there's anything else we have to do first. Yeah, we'll just go ahead and do that. So I'm going to start with this energy equation up here and just use kinetic energy 1/2 m v squared equals 3/2 kT, and we're looking at one individual particle now, so we don't have this n, so this is just the E for one particle divided by n. And if we look only at the x direction, so at the risk of being messy, what we'll do is we'll just draw an x here, and then we'll cross out this 3 and put a 1. So now we're looking at only one of the 3 dimensions, and we'll have 1/3 of the energy. Now, if we only look at the x positive direction, we'll divide this again by 2, because half of the particles are going one way and half are going the other way. So now what we have here that's over 2 right there. So Vx positive is equal to kT over 2m, and this is under a square root. Alright, so now we know what this delta V x positive here is. So let's see if we can put a few of these pieces together. We have so let's look at the pressure. We know that's the total force over the area, and the total force is going to be equal to the number of particles inside this little box. So that's going to be n, and then a ratio of the volume of the box over the volume. So that's a delta x times a over v. So that's the number of particles inside our little box. Okay, so here's the number of particles hitting the wall. Each one of them will have a force, and then this will all be over this a right here. Right, so now this little f is the force per particle. This n times the ratio of volumes tells us how many particles there are, and then we divide by a to get pressure from this total force. Alright, so we can cancel these a's right away. And I'm going to move the v to the other side. And we can see our gas equation starting to take shape. Alright, now here's the f that we need to figure out. And here's where we come back to this what we calculated up here. So we want to know the difference of momentum from one that each particle undergoes as it strikes the wall, and it'll just be 2 times the momentum that it had because these are elastic collisions and it goes just as fast coming towards the wall as it does after it bounces away. So so now looking at little f equal to the difference in momentum over the difference in time, and this difference of momentum is actually 2 times mvx, and the difference in time, as we talked about right here, that's going to be delta x over the x plus. Alright, I need to keep putting little pluses on here. So this is a delta x over the vx plus, so that will make that squared. Alright. And you know what? It looks like it's going to be even more convenient than what we had already. Maybe we didn't have to go through finding just the v by itself. We can stick with this part of the equation right here because we have this nice mvx plus squared part. So let's go ahead and substitute that part in. So we have 2, and then we have a kt divided by 2. Right, so I just took this mvx squared plus this part and this part, and put this kt over 2 in. Alright, and then divided by delta x. Alright, so these 2's cancel out, and we just get kt over delta x. Now, when we take this this force per particle and plug it back in up here, we get our ideal gas equation. So we have delta x, and then I'm going to put this in. Alright, of course these divide out. And there we have it. This is the ideal gas equation derived using classical principles. Other ways to derive it using quantum mechanics, and we'll look at that in another video most